All right. Hello, everyone. My name is Hilke Oetjen. I'm from ESA, and I'm giving the scientific presentation number 2. It is about the performance evaluation for FORUM, and the objectives are to ensure that the system designed is fit for its purpose, and also to assess the scientific maturity. And we do that through analysis of campaign data, scientific performance evaluation, and through the end-to-end mission performance simulator. So I would like to stress again that the primary mission objective of FORUM is to build a highly accurate global data set of far-infrared radiances. And the technical presentation showed that these requirements on radiometric and spectral accuracy and spectral coverage and global coverage are met at level 1. So the added value mission objectives are the retrieval of emissivity, water vapor profiles, and ice cloud properties, such as ice water path or cloud optical depths. And this is going to be shown in this presentation. So the outline here again, so I'll start with the campaign data. I need to stress again that the outgoing long-wave radiation can only be measured at the top of the atmosphere. However, the signatures in the far-infrared originating from the atmospheric state and from surface parameters can be investigated with ground-based and airborne measurements. So the objective of this part here is to test the sensitivity of the measurements, measured far-infrared radiances to water vapor, emissivity, and cloud properties. And we've done that with campaigns at the Zugspitze here on top of the mountain and from an aircraft. So we start with the ground-based. For the ground-based campaign, an instrument was built. It's called FORUM, the Far-Infrared Mobile Observation System. It was custom built during the Phase A. The spectral range it covers is from 100 to 1,000 wave numbers, so it covers the same far-infrared part between 100 and 667 wave numbers as FORUM. The spectral resolution is 0.36. And as was pointed out by Helen earlier, if you want to measure the far-infrared from the ground, you need very low water vapor, and you get that not at many locations on the globe, but so we went in winter to the highest peak in the German Alps, which is the Zugspitze, which is close to 3 kilometers above sea level. Another reason for going there is that there is a lot of auxiliary instrumentation, and one of them is the ESA, which is a commercial instrument which also measures part of the far-infrared, so it covers 400 to 300 wave numbers, but with a coarser spectral resolution. And here on the right, you can see a scatter plot of the integrated water vapor of FORUM versus the integrated water vapor of the ESA instrument. And so that black line is not the fit, it's the one-to-one line. So the agreement works really well. However, this all uses the same spectral range, the same assumptions, so to really compare, validate the data, you need independent assessments. And for that, we had, during a special observation period, some high-precision water vapor sondes, and also a little bit down the mountain, there is a cloud and aerosol backscatter LiDAR for cloud properties. So this is then now the comparison. On the left, you see the clear sky retrieval, so it's water vapor. Here, the profile. In red, you have the FORUM profile, and in black, the radiosonde. The FORUM one is an average of 19 measurements, and the radiosonde is an average of 4 measurements. I also have to point out that these sondes were launched from down in Garmisch-Partenkirchen, so not on top of the mountain. So there are some differences expected. However, here, when you look at the differences in absolute values and in percentage values, the agreement is really well. So it's from like 10% to 20% when you go a bit higher up in the atmosphere. On the right-hand side, this is from the cloud property retrieval. So you have cloud optical depth on the top, on the bottom, cloud bottom height, and green, you have the LiDAR measurements, and blue is the FORUM retrieval. And this is quite a thin cloud, very persistent, so this range is over 7 hours. And you see there is really good agreement between a passive instrument like thermos with an active LiDAR sensor. So that basically shows that we have really good information content to thin cirrus. Oops, okay. So at the end of this 2-month campaign, the instrument was adjusted from looking up to looking down for looking at snow and ice emissivity in the far infrared. And for that, snow and ice samples were collected in the vicinity of where the instrument was installed and then carefully placed under the instrument. And this was done for fresh snow here on the top and for ice on the bottom. The lines are the theoretical curves that were shown by Helen before as well. So you can see the emissivity in the model is different from one. So this is the blue line is coarse snow and ice is the red one. And we can confirm that with our measurements. So you have a distinct signal different from one. You have some features here going down and you go to the further end of the wave number scale. And so we have spectrally varying features, but and if you look carefully, you can see that there is actually a difference between these measurements and these measurements. But however, these are just 2 spot measurements, so we need more than that to really have a good idea about what is going on with the snow emissivity. So from the ground, we go to an aircraft. So this is the UK farm, and it was on that instrument airplane. There is an instrument installed which is called Tufts. It belongs to the Imperial College. It measures in the far infrared range from 800 to 550 wave numbers. It's already quite an old instrument. We're looking at one flight here from 2015 where the aircraft was flying quite close to a deck of cirrus. So you can see that here. These are measurements of a LiDAR which shows where that cloud layer is. And there are also drop sondes that were launched at the same time. So we have from those sondes the temperature and the water vapor mixing ratio. So all of this happens within 1 minute. So we have quite a well-constrained atmospheric state here. And so we use this to then check whether we have information content in the measurements of the far infrared with respect to the crystal shapes of the ice particles. And for that, we plot the difference between measured radiances or measured brightness temperatures with simulations, and these simulations were done for different kinds of crystal shapes. And so then these are the different colored lines. This is then plotted for the mid-infrared and the far infrared, and the white areas are where there are sensitivity, where there is sensitivity to cloud. It's quite a complicated plot, so I just want to highlight some areas. So when you look at the mid-infrared, you see, first of all, that all these lines for the different crystal shapes lie on top of each other. That means there is no sensitivity to microphysical properties. Also, you see that they are all within the measurement uncertainty, which is the black dashed line. If you go to the far infrared, the picture is really quite different. You can see that these different colored lines have different values, and they lie outside the measurement uncertainty partially, here really a lot. And also some of the signals are positive and some of them are negative. So the question was, can current ice microphysical models fit observations across the full infrared? And the answer to that is no. So this really highlights the need for level 1 radiance measurements covering the full far infrared and mid-infrared for developing and testing parameterizations that are then important in climate and numerical weather prediction models. And also it shows that we need spectrally resolved measurements. So during that campaign, there were only flights over clouds. So we flew again this spring and over clear sky, so in clear sky. And so this is really new analysis. So this is retrieval of water vapor. And so the first guess of the retrieval is the red line. And the blue lines, the green lines are the retrievals, and each line is is like a scan of about 1 second. And the blue line is the dropson, so it's the water vapor profile from the dropson. And you can see that, so that the retrieval is really distinctly different from the first guess. So we definitely have information content with respect to water vapor, and also quite low water vapor. And also, you can see these little features here showing up in the retrievals. This was all we had for campaign data. So in summary, we have good sensitivity to atmospheric variables, but we have only spot measurements during phase A, so there is a need for global satellite measurements. So in the next part, we only talk about simulations. So this is the scientific performance evaluation done by validation, and we split it between cloudy sky and clear sky. Again, so the experimental setup is a set of 212 atmospheric profiles with single-layer ice clouds, and they come from this ECMWF diverse data a profile database. And so in there, ice clouds are described by the profiles of ice water content. The location of these samples is shown here in the plot, and it's color-coded with the ice water path. And so 1 gram per square meter, everything below is a subvisible cloud. And maybe to put that into perspective, a sugar cube is 3 grams. So if you spread a third of a sugar cube out on 1 square meter, that is the amount of ice we're talking about here. So what we do then with this data set, we do simulations with RTTOF. RTTOF is the model of the EUMETSAT numerical weather prediction and satellite application facility, and it was updated to simulate FORUM radiances. And then to these 8 radiances, the noise is added. And then the ice water path and cloud top and cloud bottom height are retrieved. And so this is here one example where you have the true cloud here in orange. And the first guess is that green box, and it is a box because we assume that the cloud is homogeneous. And at the end of the retrieval, we get this red box, so with the error bars for cloud top and cloud bottom, so these agree very well. And also here the ice water paths of the truth and the retrieved agree well. And so this is here then in radiance space. So the first guess is the green radiances, and then the retrieved one is the red, and the truth is behind it, so you can't see it. So then we've done that for all of these 212 cases and retrieved the ice water path. And so in this figure here, you see is like a scatter plot of the retrieved versus the truth. And the dashed lines are the Oscar threshold and Oscar goals. And so the FORUM goal, the FORUM requirement is the 20 grams per square meter. So the green line, however, we are performing that well that we can constrain ourselves to the goal actually. And so you can see that 90% of all the cases fall within the threshold requirement for ice water paths, level 2 requirements. And these are all subvisible clouds, all this data here. So if you then look at the cloud top height of that same retrieval and you plot the retrieved versus the truth, again, this is now color-coded with the ice water path. So everything green and blue is subvisible. Then you see there a lot of red dots lie on the one-to-one line, and there are a lot of blue and green dots out of it. So if you remove them, so if you remove everything with ice water path lower than 1 gram per square meter, then you have 71% of successful retrievals. We have to point out that in this data set, there is a bias to subvisible clouds, so this does not exist in the real atmosphere. So more than half of the clouds in this data set are subvisible, but in the real world it's only 9%. So for the clear sky, we look at the two components of the uncertainty. So this is the systematic uncertainty and the random uncertainty. So first we're looking at the systematic uncertainty. So you get systematic uncertainties from knowledge errors or flawed assumptions in your radiative transfer code or your instrument. And so the parameters studied here are not including interfering gaseous species in the radiative transfer model, the spectral resolution of the radiative transfer calculations, and incorrect spectral knowledge of the instrument, and the knowledge of the state-of-the-art spectroscopy. And so the radiances were simulated and then convolved with a FORUM spectral resolution for this. And so this is a really complicated plot, but so you have on the left-hand side the absolute error on the emissivity and versus the wave number. So the far infrared range is here, and the scale is logarithmic. So it looks dramatic, but it's not. But the most important line you want to look at is the black dashed line, because this is the systematic uncertainty component on the emissivity retrievals that comes from the radiometric accuracy. So we can't do anything about it because this is just how the measurements are. But everything below is basically negligible because of that. So we can for now remove all the trace gases. Then we still have some curves here, but it's orders of magnitude lower, which comes from the spectral resolution, from the spectral knowledge of the instrument. But since emissivity is varying smoothly with wave numbers, it is not very important. However, what is important is these two curves above the radiometric accuracy. And both of them come from uncertainties in the water vapor. So one of them is the spectral database, so the line parameters, and the other one is the water vapor continuum. And so the requirement for the uncertainty on the emissivity is 0.01, so it is here. And so the conclusion is that we need to improve the spectroscopy and the water vapor model before we can reach our requirement on emissivity. However, this is a good thing because this is one of the goals of the FORUM mission. And this figure then shows then the same plot, but for the water vapor profile. So now the uncertainty is on the X range, so it's in percent. And here's the altitude. Again, if we remove the trace gases, we have here again the absolute radiometric accuracy line, and then we have these two lines for the spectral database and the water vapor continuum at about quite large values. So that means, since we have this difference, that the FORUM's radiometric accuracy is adequate to improve spectroscopic parameters and models. And so then numerical weather prediction climate models will benefit from this improved spectroscopy we can get out of the data. So for then we need to, so this was only one component of the uncertainty, so now we need to look at the random uncertainty. So for that, we look at, we do a Bayesian approach, also again for water vapor and emissivity, And so the high-resolution radiances were simulated with the radiative transfer code again, then convolved with spectral resolution, and then the threshold, goal, and noise were added to them. And the a priori uncertainties that are considered here are the ones that are used by the UK Met Office to assimilate EASI spectral radiances in their operational numerical weather prediction models. And these basically present our best knowledge of the atmospheric state. So here on the left, it's the uncertainty water vapor. On the right is the uncertainty for emissivity. So we have here for water vapor, again, as profiles. The a priori uncertainty is the black line, and then the retrieval uncertainty, so the random uncertainty, are the colored lines, and the difference between goal and threshold are the solid and the dashed lines, so there is not much difference. Because it's a percentage uncertainty, you have low water vapor and polar regions, so then the uncertainty is larger, basically, but it is all within the requirement of 15% in the UTLS for FORUM. If you look here at the right, and you should only look at the blue line, the polar line, so I would like you to recall that the requirement is 0.01 for the uncertainty on emissivity, and this is somewhere down here. So when you look at the blue line, so in polar regions, the requirement on the far infrared emissivity can be met between 410 and 600 wave numbers. However, if you do then a synergistic retrieval, so you use FORUM radiances and augment them with EASI NG retrievals, you can see here, so FORUM alone is red, and EASI plus FORUM is blue, so this is again the uncertainty on the emissivity, and all of a sudden, although EASI NG doesn't measure in the far infrared, the uncertainty reduces a lot, and that is due to the fact that the retrievals benefit from a better surface temperature constraint. So in this case, then the requirements can be met over the whole range between 300 and 600 wave numbers. And so when you look at this case here for the water vapor retrieval, so this is one of the worst cases because it's a dry Antarctic winter, so we're at 15% water vapor uncertainty, and you don't see much improvements when you do a joint retrieval with FORUM and EASI together. So as a summary of this part of the presentations, measurements and simulations were applied, confirming that the FORUM performance is fit for its purpose. For clouds, key physical parameters can be retrieved. Water vapor spectroscopy and continuum models can be tested and improved. Far infrared emissivity of snow and ice can be retrieved. And water vapor profiles can be retrieved in the upper troposphere, lower stratosphere, complementing EASI NG. And so now we're coming to the last part of the presentation, which shows results of the FORUM end-to-end mission performance simulator. And so this is the intermediate basic architecture overview of it. So we have these different modules here in the middle: the geometry module, the scene generator module, the observing system simulator for the imager, the observing system simulator for the sounder, and then the level 2 module. And so you start the chain with giving the simulations a geolocation and a time, and then the modules in the chain will produce an output, which are then the input to the next module. And all these inputs and outputs are also collected and assessed in the performance assessment module, where then automatically the inputs and outputs are compared. A bit more details. So the scene generator module can process heterogeneous and homogeneous scenes. If we have heterogeneous synthetic scenes, we can add to like 2 levels of heterogeneity. It could be either cloud or surface. So this sketched here, you can put a knife edge through it, or you can insert a circle. So this outer field is the field which the imager would use, and then the lower, the round one is the sounder with some extra area around. And so also modus data product-based input scenes can be digested, and here's an example of 3 scenes we looked at, which is over the UK. 2 of them are over clouds, 1 of them is over clear sky, so this is just the cloud effective radius. And on the right here, so that's the surface temperature for this one clear scene, and you can see the level of detail that can be processed in the scene generator. And also these grids are also fully configurable to the applications we want to look at. So the instrument module, it's quite complicated because there are lots of effects that have to be included. So the effects that are included are the finite field of view and the consequent beam divergence inside the interferometer, resulting in this wave number dependent instrumental line shape. Errors induced by line of sight drifts by interpolating between a set of interferograms. Calibration, black bodies, including uncertainties on temperature and emissivity, transmission and reflection coefficients of optical components and wavefront uncertainties, detector noise, detector response, and spectral sampling errors and digitization noise. And the instrument module also includes the level 1 processor, which is then what the level 1 processor encompasses: interferogram zero pass difference correction and phase correction, radiometric calibration functions from hot and cold reference black body spectra, measurement of noise propagated through the instrument simulator chain, and we also have a separate module that simulates then the instrument line shape, which is then used in the level 2 module. And for the imager, the effects that are included are the optical point spread function, the instrument spectral response, the radiometric noise, calibration uncertainty, and attitude errors. So, and this is an overview of the level 2 processor. So you have an input of the level 1C spectrum, so the sounder spectrum and the image, and some auxiliary data. And so the first part of that level 2 processor is a machine learning algorithm that detects whether the scene is cloudy or clear, and it also then classifies the cloud type into cirrus, ice, or liquid. And depending on how that scene is classified, different paths are gone through in the processor. So if it's a clear scene here, then we perform a water vapor profile retrieval, and we also retrieve some auxiliary parameters. For the cloud, then it splits for a liquid cloud, then you only look at the cloud top height, and in some cases you can get some cloud optical depths and cloud effective radius, but for cirrus and ice clouds, the main target for clouds for FORUM, you get the cloud optical depth, the cloud top height, the cloud effective radius, and from the radius and the optical depths, you can calculate the ice water path. And so this then writes an output file. So the test scenes that were run through that simulator, so we have 12 key scenes representing a wide range of realistic conditions, and so 6 of them are cloudy, so they are described here. We have 3 cirrus clouds, and we have 1 very low marine stratus, so a liquid cloud at 1.25 kilometers, so it's a challenging case for FORUM. And we also have 2 thicker ice clouds. And so these are the 6 cloudy scenes, and then in order to compare them, we just take the clouds out and treat them as clear sky. And we looked at these 3 modus-based data scenes that were shown earlier in the scene generator. So if you put that through the end-to-end simulator, you get these radiances here. So this shows the range of what we get in the level 1. These are all the clear cases, so the 6 clear cases plus the 1 clear modus. And if you convert that into brightness temperatures, then again here you have the clear cases, but then here on the right we show the difference in the brightness temperature between clear and cloudy. And so you have like the range here from one cloud where you have very little difference, which is the marine stratus, and then very large difference for like a really thick cumulonimbus cloud. And here on the left-hand side also you can see the whole range of temperatures that you encounter with lower than 200 and higher than 300 Kelvin. This is the output of the imager, of the instrument module for the imager. So you can see that level of detail versus the 2 cloudy scenes from MODIS, so show realistic 5 minutes. So it shows the realistic level of complexity of the imager module. So now the level 2 module starts with these scenes, and so the first one is the machine learning cloud detection. And so these are all these cases, and everything that is green is good, and the one red case here is the tricky cloud we knew we would have problems with. And so what we then also did, we took these cirrus on desert, cirrus on ocean, and cirrus on snow ground, and reduced, just we kept everything else the same, but we reduced the optical depths until the cloud detection algorithm could not detect that cloud anymore. And so these values here are quite low, so subvisible clouds would be optical depths of lower than 0.05. So in some cases we can detect those subvisible clouds. Over the snow it is difficult. You have a larger false alarm ratio just because you have a cold cloud over a radiatively cold surface. So then the actual retrieval starts, the inversion, and I'm only showing here the ice-water path. You always have here the ice-water path in logarithmic scale because the cumulonimbus is out of scale here. In blue is always the true that goes into the scene generator, and then the lighter shades of blue show the results for the 2 different instrument concepts, A and B. And so if we take out the thick clouds and leave only the cirrus clouds, we can say that all the requirements are met for cirrus clouds, and all the results are consistent for the different concepts. And so we are going to do some statistical analysis for determining the representativeness of these results. So the other thing we've done, you can only do this with the end-to-end simulator, is to look at the knife edge scenes, because this is then interpolated in the interferogram space. So we look at 100% cloud cover, and then we have 95% cloud and 5% clear, 90 cloud, 10% clear. And then we look at the difference between the true ice-water path and the retrieved, and down from 100% to 80% cloudy. And because this is such a thin cloud, we are all within the requirements. And so we want to include this also in the statistical error analysis. So this is like the clear sky result for the 6 cases. It's the profile retrieved minus the truth. All of them are within the 15% requirement we have on the water vapor. Okay, so these are the results. Now is the assessment of scientific maturity. It is very important that we reach SRL 5, scientific readiness level 5, at the end of phase A. And so for that we have to answer these questions here, and the evidence for that provided is in the report, and we also provided that here in the presentation, so I'm not going through them, but I can tell you we're ticking all the boxes. So then the next step is reaching scientific readiness level 6. So far the phase A studies have shown that FORUM has the capability to deliver level 1 and level 2 with a required accuracy over the range of conditions that the mission will encounter. And the roadmap will be to further develop the end-to-end simulator to also include surface emissivity and long-wave radiation fluxes. We need to build an airborne demonstrator for the FORUM concept. The FILMOS instrument will be adapted to be flown on a balloon. The synergies with other instruments need to be further examined, and also RTTOF will have to be developed for the chosen concept, because this gives us a chance for really fast retrievals. And these activities will ensure that we can reach SRL 6. And so in summary, FORUM is a unique mission which for the first time will make measurements of the Earth and the far infrared part of the spectrums in space. With climate change becoming an increasingly important issue for governments to understand and attempt to mitigate, FORUM is a timely mission as technology has advanced to a state where these measurements are now possible. And FORUM will provide new insights into atmospheric and surface physical properties to improve climate models, and hopefully FORUM could influence the design of future operational Earth observation systems. And as this region of the emission spectrum has not been observed before, there may well be surprises that come to light, and all the FORUM objectives can be met.
Thank you. So after the exhaustive presentation of the scientific and technical aspect of the mission, I will provide now an overview about the programmatic assessment. Starting with the critical areas and technology maturity status, FORUM is considered a technically feasible mission, as with the evidence has been provided in the course of particularly of the technical presentation, but challenging within the programmatic constraints applicable to the E9. For the satellite platform, both concepts are based on extensive reuse of heritage and technologically mature design. For concept A reuse of the platform developed for the Copernicus Sentinel-5P and the Astrobus M family has been proposed with minor modification. For concept B, the platform is based on heritage design that are either flight-proven, capitalizing on the Proteus standard platform product series and the Copernicus Sentinel-3, or under advanced development status in the context of the FLEX Earth Explorer 8 mission. In the case of concept B, a custom platform structure will be developed for FORUM. So despite some platform units will require a mission-specific adaptation, all the custom designs are based for both concepts on mature technologies, which has already reached a TRL higher than 5, and therefore do not require the implementation of early pre-developments. For what concerns the FORUM payload complement, the FSI and the FEI, in both concepts, a reuse of mature technology with heritage from flight-proven instrument design has been proposed. For the embedded imager, no criticalities have been identified. For the sounding instrument, the interferometer reuse with mission-specific adaptation, the design of the FTS that is flying on board the GOSAT-2 mission. Nevertheless, the unprecedented spectral range of the instrument and the demanding performance requirement led to the identification of critical areas requiring specific technology development to reach the TRL 5-6 by the end of phase B1 as required. So this table is providing an overview of the pre-development activities that were introduced by Charlotte during her talk, and that I will address shortly in the next slides. So what is important to notice in this table is the starting TRL at beginning of phase A, what has been achieved at the end of phase A, which is for all areas in equal or in excess to TRL 4, and most importantly that the planned pre-development will allow to reach the required TRL 5 by the end of phase B1. So starting with the interferometer mechanism for concept A, the heritage from the existing breadboard that you have actually seen on display during the coffee break allowed to consider the TRL at level 4 already at the beginning of phase A. So the activity that has been carried out is the consolidation of the design adaptation from this existing interferometer for the specific forum needs, and the procurement and testing of the units required for a breadboard implementation. For concept B, the activities to reach TRL 4 during phase A consisted in the manufacturing and assembly of an interferometer mechanism that you see on the picture on the right. So this breadboard has been manufactured and assembled, the functional tests have been performed, the mechanism has been characterized for behavior under microvibration, and speed stability tests have been completed. For the interferometer mechanism, in order to reach the objective TRL 5 during phase B1, the mechanism will be assembled and integrated in a breadboard, an elegant breadboard for concept A, and will be tested for performance under representative environmental conditions. A similar approach will be followed for concept B with integration of the mechanism in a complete interferometer assembly, including the beam splitter, the detectors, and the laser metrology, and characterized for performance under relevant conditions. For what concerns the beam splitter, pre-developments have addressed different technologies leading to the selection of a baseline for both concepts that has been raised to TRL 4 to 5. And also dedicated pre-developments have been conducted on alternative technologies. So as mentioned by Charlotte, the selected baseline consists of dual wedge diamond plate with germanium coating and anti-reflection treatment on the other side for concept A, while for concept B, the other side consists of bare diamond with an option to assess also the performance with an anti-reflection treatment. The picture are showing the beam splitter implemented for the baseline technology, a diamond sample, and a full-size diamond wedge plate. For the alternative technologies, membrane, polypropylene, and mylar have been considered. Only the latter has been retained as a potential alternative solution after the first characterization test. The polypropylene, due to the result of the initial manufacturing and characterization activity, will not be retained. This table, which I will not enter in detail, is showing all the activities that have been carried out on the baseline technology samples for both concept and for concept B, also on the full-sized wedge diamond plate, which includes the performance testing for what concerns the characterization of the transmission and reflection property over the full spectral range. Performed not only on the samples but also on the full-size wedge plate for concept B, and the relevant environmental testing that have been performed for concept B, allowing to reach a TRL between 4 and 5 due to the non-complete environmental testing performed. One important point, as recalled by Charlotte, is that the result of this test have been used to characterize the achievable performance of the instrument. For what concerns the detection chain, both concepts have reached the objective TRL 5 by prototyping and manufacturing detection chain with a representative detector for noise and detectivity characteristics, and characterizing their performance in terms of noise and responsivity. So you see the picture of the relevant breadboard and test setup. So all activities have been completed, confirming the TRL 4. Also in this case, results of this characterization activity have been fundamental to assess the performance, the achievable performance of the instrument. For phase B1, the objective is to reach TRL 5 to 6 by procuring and testing in a relevant environment flight representative detectors, including the relevant front-end electronics, assembling then the full detection chain and integrating and testing in the complete interferometer assembly. For the black body, the various activities have been mentioned by Charlotte during the presentation. So the first part of the activity consisted in selected a baseline for the coating materials that have been characterized for emissivity over the full spectral range of the instrument. You see a picture of the samples and the lab setup for the emissivity characterization that have been completed. In parallel, a model of a design performed for the blood body cavity has been completed to characterize the emissivity performance. For concept B, the samples, coated samples, have been submitted to environmental testing, including humidity and thermal vacuum cycling. And black body geometry prototype that you have had the opportunity to see on display during the coffee break has been developed in order to validate the coating deposition process. For concept A, a phase change cell breadboarding and testing has also been completed in lab environment. Now, for the phase B1 objective, the objective of TRL 5 to 6 will be achieved by designing and manufacturing a flight design cavity and testing it in a relevant environment in order to confirm the achievable performance in terms of temperature homogeneity and achievable knowledge of the temperature and emissivity for the baseline coating selected. For concept B, there will be dedicated development during phase B to raise the TRL of the pointing mechanism solution that has been identified. This will consist in the design and manufacturing of the mechanism and the relevant testing under representative environmental conditions, including thermal vacuum and vibration test. About the development approach, FORUM will follow a traditional phased development approach with phase B, C, D, and E1. The platform and the instrument development are decoupled as much as possible. For concept A, the platform will follow a direct prototype model approach. The mechanical and thermal qualification will take place at satellite PFM level. The instrument-to-platform interface will be verified on a functional test bench, and the full qualification of the instrument-to-platform interface will take place at satellite level. For the instrument, also a PFM approach is proposed with an electrical functional model for the verification of the electrical and functional interface at instrument level and also at payload platform interface verification level. The instrument electromagnetic compatibility, the mechanical and thermal qualification, as well as the performance characterization in this case will be achieved during the satellite PFM testing. For concept B, an approach integrated with a satellite structure and thermal model has been planned for an early mechanical and thermal qualification. An avionic test bench will be used for the early verification of the design, hardware-software interface, and will be further extended into a functional test bed to complete the verification at satellite level and the verification of the payload platform interface using an instrument engineering qualification model. For the instrument, in this case, an EQM-FM approach is proposed for all subsystems, meaning that full qualification will be achieved at subsystem level. The instrument engineering model is also included for the rehearsal of the integration and alignment procedure. So in this case, the instrument prototype model will have achieved the full qualification and characterization prior to the delivery for integration in the satellite PFM. For what concerns the development schedule, the schedule is driven by the instrument development after the preliminary design review, and therefore by the phase CD. A launch by the end of 2025 is not considered feasible with adequate margin. A launch by mid-2026 is assessed as feasible but challenging and requires an optimization of the development approach and the related schedule, taking into account the associated risks. This simplified Gantt chart shows the assessed feasible schedule with a launch by mid-2026, assuming a start of the development activities at the end of the first quarter of 2021, with a relatively short phase B2 and a combined phase C and D duration slightly exceeding 4 years. So to conclude, considering the outcome of all the preparatory activities that have been carried out within a compressed and very tight schedule, it is judged that the critical scientific areas of maturity and risk have been assessed, and there are no major issues concerning the scientific development of the FORUM mission. The required SRL of 5 is considered to be reached at the end of phase A. Assuming an expected successful outcome of the ongoing and planned technology pre-developments, the maturity of critical technology will reach the required level of TRL equal or higher than 5 by the end of phase B1. The development schedule is compatible with the launch in the 2026 timeframe, and therefore the FORUM mission concept is considered sufficiently mature for implementation as the 9th Earth Explorer. And this concludes my presentation. Thank you for your attention.
I just want to, so we just want to...
Now we have chairs, put the chairs on the stage, right?
And we still have, yeah, that slide. Sorry, I need to acknowledge everybody who put a huge effort into getting where we are. So this is just a small fraction of the people who were involved with getting us to the end of this presentation through the question and answer session. And so thank you so much.
So now we need 1 or 2 minutes patience. In the meantime, I will try to explain the procedures with the question and answers. I hope you have written down your questions. We are a little bit late, so maybe we can cut some 5 minutes from the question and answers to FORUM part. There will be 2 microphones to the left and to the right. These ladies here will serve you with the microphones. Thank you very much. There is another catch box here. I will not throw it. Michael will throw it. He is better than me. You may guess what's in there. There's a microphone in there. So if you're in the middle, please raise your hand and you will get this catch box from Michael. So I will retreat. Hilke, you will moderate the discussion session.
We just put the backup slides.
Okay, let's not open them though. Yeah. Well, let's just wait with the questions. Let's not fuss with that. Do we have everyone on the stage? Okay, Bernardo, I think Charlotte as well, since you presented. So now we have about 25 minutes left for question and answers. This will cut short once the time is up. Please wait until you get a microphone, and also please could you introduce yourself with your affiliation so we can note down properly. The mic numbers. Oh, okay. side note. Okay. All right. Any questions?
Yes, hello, I'm Ad Stoffelen from the Dutch Met Office. I work on spectrometer, Aeolus, and also involved in Earth Care missions, developing level 2 processors. And my question goes to, I think, the beginning of the talk, where you talk about uncertainty in climate models, GCMs. And I think also the suggestion was given you could reduce uncertainty of climate projections by about 50% or something like this. I'm not sure. Anyway, your idea is to reduce the uncertainty. And my question, what I missed in the presentation is, let's say, the scope of how you're going to, or what will contribute to reducing this uncertainty. And I can further qualify this, maybe. Given it's about balance. You're talking about balance of radiation. Given the sampling, I don't think it's a monitoring mission. It's a mission that is more focused on looking at processes. And you're looking at certain processes and you want to reduce uncertainty in parameterizing them or capturing them. There's many processes, also some are not related to radiation. So I'm more looking at the dynamical processes, ocean drag, land drag, moist convection parameterization. And there I also see biases in GCMs. I don't think you will address those. So you will address some other ones. And the question is, how can you have a vision of how much you can reduce those uncertainties in climate projections?
I can say a few words add on that. I mean, I guess there's, I mean, I've spent...
Can you introduce yourself? Sorry.
Oh, sorry, I'm Roger Saunders from the UK Met Office. Yeah, and I've spent the last 25 years trying to use satellite observations to improve our weather forecasts, both through the initial state and the accuracy of the NWP model itself, through improving the physical processes. And clearly over those 25 years, as you well know, we've improved the accuracy of those weather forecasts. So I think the same should apply to climate models now. We need to improve the physics in the climate models. And there are 4 key areas that we identified, I think, in our talk today. Firstly, on the radiation, currently we're just guessing what the far infrared radiative transfer fluxes in our model are. We've got no real validation of that at the moment, no measurements. So that's an area we will be able to validate and improve. Secondly, on the cloud physics, clearly we're going to get better understanding of the cirrus radiative properties that will represent in our models. And I should say it will be both the climate model for the Met Office anyway, where we have this unified model. It benefits both the climate model and the NWP model, as it's the same model. Thirdly, we've got the water vapor, upper tropospheric, lower stratospheric water vapor. All the information content studies we've done show there is more information than we get from YASI alone by adding FORUM in there. And that's an area where the models are quite large spread at the moment. And that should feed back into the dynamics. And the fourth area, of course, are the surface properties in the Arctic, where currently most climate models assume an emissivity of 1, and clearly that's not right. So I think we have to make all these improvements to the models. It's not going to happen all in a big bang. We're suddenly going to see improve. It will take a while. We'll have incremental changes to the model based on FORUM and other satellite data, but FORUM I see as one of the key tools that we can use to improve the climate models.
Maybe I can add a little bit to this. Martin Riese from Forschungszentrum Jülich. I think the main advance is that you have the observation of water vapor, for example, in the UTLS, but you have also at the same time the signal of this water vapor on the outgoing long-wave radiation. So you have the direct link between the composition and the climate important effect, the radiation that is outgoing. And I think to confront models with both of these aspects is very important. And then you can maybe select which climate models are doing a better job in already representing the water vapor distribution or the cirrus distributions. And of course, you would have more confidence that these models also predict the climate better in future, or models that have deficiencies, they can improve. They can think, why don't we, let's say, represent the water vapor distribution or the outgoing radiation in the same way as is measured by FORUM. So this would be confronting with models. Another aspect is that we can extend long-term time series, for example, water vapor time series from the SWOOS data that go back like 20, 30 years. And now we have a very accurate new data set that can really extend these data sets. So we have a long-term data set. And we can also, let's say, probe feedback effects by variability that is measured. And we can look how well models are doing in capturing these.
Right, okay. Jackie McGlade, I'm here as part of ACHIO. So just to follow up on that, I mean, I'm going to be brutal now. I mean, would you say then that FORUM is about refining, or is it genuinely about doing something different? I guess that's really I want to see how far out you're going to push the borders. You're saying this will add incrementally to our ability to improve, but is there in the back of your mind a sense that this is actually going to be a sort of breakthrough science and give us some completely new physical understanding?
Yeah, I think it's really fundamental because it's of course refining, but we need to refine to reduce this large uncertainty that we have in the predictions and in the feedbacks. And now we have a really new piece of observation that really helps us to narrow this arrow down, and this is really new piece of information. But maybe
I can add to that. So Stefan Bühler from University of Hamburg. So in my view, the really new thing is that this opens up a completely new spectral view on the climate feedbacks. And so far, I mean, we have EASI, but it's not capturing most of the frequency range where the water vapor feedback and the cloud feedback actually happens for high cloud.
Andrew Watson from the University of Exeter. I'm here as part of ACHIO. As I understand it then, this is not really an operational, you're looking at processes, you'll be using the data to improve parameterizations, which then are used in climate models, because climate models don't have the high resolution spectrally that you have, so they have to use bands, for example. Now, it seems to me then that variability, if you're developing parameterizations for the variability, is absolutely key. And I'm interested in that the lifetime that you're planning is 4 years, which seems to me, though you said this will get interannual variability, it actually is not long enough to get interannual variability at the ENSO timescale or some of the other climate modes. So I would like you to comment on, well, why are you planning just 4 years, and what do you think about how you're going to really capture interannual variability?
I can attempt to answer this question. I mean, both the water vapor feedback and the cloud feedback, the feedbacks themselves are fast. So they clouds and humidity respond quickly to changing surface temperature. And the natural variability in global mean tropical surface temperature is around 1 Kelvin. The spectral signals that are associated with that variability, they are well above the noise. So we will be able to detect them with FORUM. So we can see the feedbacks in action on the natural variability.
Maybe I can add to that. So we have for maybe 6 years. And of course, it would be beneficial if you have an El Niño because it gives you a strong signal. But as pointed out, also the natural variability. So we've looked at that, for example, between 2012 and 15. In the upper troposphere, also in water vapor, in the tropics, like 5–10%, and the temperature variability is well above a Kelvin or so. And that can also be used, of course, let's say, to probe the feedbacks. Of course, it's beneficial if you have strong signals, and we have a good likelihood to have that, but of course, no guarantee.
The hope is it will be longer than 4 years, 6 years as was quoted, so I think hopefully we will get all the variability we need.
Then also, if I may complement, as you see in the technical presentation, we've designed the spacecraft for 4 years, but we have margins if we fill the tank to last 2 more years, maybe more, depending on how it works.
There were some questions in the back. Yes, please.
Okay. Is it on?
Yes.
Evgeny Aksin of National Geographic Center. I'm ocean modeler mostly, and modeler for the polar areas. My question is, you mentioned validation and calibration of the mission for different conditions, different underlying surfaces, and you also make assertion about the polar areas being very important in your investigation. I haven't seen much comments of the validation in the polar areas. I saw the high mountains, I saw the different tropical areas like Mediterranean. I haven't seen much of the polar areas. Could you please comment on this?
Validation. Helen?
Okay, I'll give it a go. So, I mean, one method of validation that's very common is simultaneous nadir overpasses. They will predominantly happen in high latitude areas. So if you look at the coverage, the repeat cycle is faster. There's greater coverage at high latitudes, and that's also where you'll get cross calibration with other satellite instruments. Some of the flight campaigns that we've already done we haven't shown them here because they weren't funded by ESA, but they were actually done over, for example, the Greenland ice sheet. And we've been able to show that from high altitude aircraft measurements, you can actually make the emissivity type retrievals that we want to perform with FORUM. So the sorts of things that you would do is to try to coordinate your flight campaigns over high altitude sites such as those available at Barrow, possibly at Summit, all of those locations which have good ground-based instrumentation that you can then compare your retrievals with the underlying characterization that you've got from the ground-based sites. And you can also look at using the information that you have from the ground-based sites to forward model what you would expect to see from your aircraft campaign and also from the instrument flying over the top. So you'd have the top of the atmosphere radiances, the flight level radiances from an aircraft or a balloon, and then you'd also tie that with the by performing the characterization over locations which have the ground-based sites, the ground-based information as well.
I can perhaps add that while this is new for the far infrared, I mean, surface emissivity retrieval has been done in other frequency ranges successfully, for example, in the microwave range or in the sub-millimeter range with basically the same scientific approach that we will be using.
There was a question over there.
Yes, I'm Tony McNally. I'm from ECMWF, where I'm a principal scientist. The question I have for the team is that with the footprint size and the sounder that you have, you're typically going to get fully clear scenes around 10% of the time, no more. Really, 10% is an upper limit. And in the 15 or so years that we've had hyperspectral sounders, nobody has demonstrated a robust way of extracting humidity information in the presence of clouds. Would the team like to comment on whether they have a strategy to extract high-quality humidity information in the 90% of the situations which would be cloud contaminated?
I think there are techniques to, as you well know, Tony, to measure humidity over uniform low cloud. So I think we have some hope, and uniform low cloud does make up a large proportion of the cloud that we see on the Earth. Obviously, the techniques you and others have developed for YASI, we would apply the same to FORUM. I don't know that, have we done any, I'll look at Marco who may have done some retrievals on this.
Yeah, I'm Marco Ridolfi from University of Bologna, and during phase A studies, we actually tried some test retrievals from using simulated observation, of course, and we tried to retrieve simultaneously the profile of temperature, profile of water vapor, surface temperature, surface emissivity, and also we tried with cloud properties all together. Cloud properties, we tried to retrieve ice water path, cloud top height, and cloud bottom height. And we found that the retrieval is possible. Of course, the quality and the error on the retrieved profile, especially also on humidity, depends on the cloud optical depth. And so if you have a very thick cloud, this is not possible. But if you have a thin cloud, optically thin cloud, this is possible. And especially if we exploit the synergistic measurements of YASI and G, which has a very good signal-to-noise ratio in the middle infrared, it is possible to exploit both spectra to do a synergistic retrieval and to get good accuracy in the profiles.
And also there are recent publications where they exploit the full far infrared and thermal infrared spectral range, where you have opaque cloud to retrieve water vapor on top of the cloud. So the profile on top of the cloud can always be retrieved, provided that you have good information about the cloud underneath. So I think that you can retrieve water vapor in any case. The only thing that is limiting the cloud is the vertical range where the retrieval is possible.
Okay. There was a question here.
There are some examples included in the report.
Thank you. Stephen Briggs from GCAS and Reading and Cambridge Universities. There's a strong science case for this, clearly, and it's the case which has been made for probably best part of 30 years for such an instrument. Clearly, something must have changed in the technology. Why is this being proposed now as a feasible instrument when there have been difficulties since at least 30 years in doing this, when the science case has been strong during that time, I think?
Yeah, if I can take this question. Have you seen in the presentation we've done a very large investment of work in technology development, mainly on the area of the beam splitter and on the black body cavity. And actually, if we focus on the beam splitter, I think this is the key element for the mission. We tried 3 different types of material. Polypropylene, because also the particularities of FORUM is that we need to split the beam from 100 wave numbers to, can you hear me?
Yep.
Yeah, okay, sorry. To 1600 wave numbers, so it's a long spectral range. And we need to split it with the same efficiency. We want to do it in the whole spectral range. So this is not easy. And there are not very much materials that can do this. So we tried them all. We tried polypropylene, which was used, I think, in some mission to Jupiter for some similar purposes, but not in the same characteristics as FORUM. We tried also mylar, and also we tried the diamond material. We have to say that for the polypropylene with the characteristics that we needed in terms of coating and the mylar, we didn't succeed. We tried and we succeeded. We manufactured it, we mounted it, but we tested it and the performance was not what we expected. So we discarded this. Then it remained the only material which has very good properties along the spectral range. But just to give you an idea, because I think the important, and I think Luca mentioned in his presentation, is that we want to do it with a specific accuracy. For the big sample that you've seen in the presentation, that's at this moment the state of the art, or how big we can manufacture a beam splitter of this size. So now we are at the moment that we have this, I think this specific and particular technology ready in order to do what we want. Also, just to put another example, in terms of a feasibility assessment, there has been a mission from NASA that it is called OSIRIS-REx. It was launched a couple of years ago. That it is embarking also a Fourier transform spectrometer, I think with not exactly the same spectral range, but it is also using this type of beam splitter material, smaller, and it was very recently. Then if we also go to the coating, again as well, this was also, in my view, a technology important new development. We've also tested many materials, and we have one that it is actually good for the job. Huh? Also, there have been new materials that can give you very good properties in terms of emissivity. Also, another important thing is that we've been testing it in relevant environment for the full spectral range. But actually in Europe there is only one facility that it is able to measure in vacuum from 100 wave numbers to 1600 wave number, which is the Metrology Institute of Germany. And possibly in the world maybe there are only 2 or 3. So I think these are the 2 key elements. But also combined with what the scientists are proposing in terms of performance was prevented.
Can I add this? No?
Maybe we should go to the next question. We can address that tomorrow again if we want to discuss more. Okay.
Jacek Piskozub, Institute of Oceanology, Sopot, Poland. Thank you for the great presentations. I listened to that, but I was a little surprised by some claims about what the mission can do for things like weather prediction or climate sensitivity. I now understand that it's mostly through the optical parameterization, long-wave optical parameterization of the models, but the things are not only optics, it's also dynamics. You know, for climate sensitivity, you need to know how much the low clouds will change, how clouds will change, where and when. And do you have anything? Do you plan anything in this mission to say something about the dynamics of the atmosphere? Thank you.
We lost the microphone, sorry. Well, perhaps I'll just start. Obviously, understanding the water vapor field is one area where the monsoon circulation is still uncertain in models, and we hope that will improve the dynamical representation in the models. So I think that's one specific example you can give, but obviously the balance in the models is governed by the radiation and the clouds, so it will come indirectly. Let me say, Martin, say a few words.
And you've also seen the view graph of Helen, that upper tropospheric water vapor is so important for cooling, so it really influences the thermal structure of the UTLS. And then, of course, let's say like the jet stream or so, is the thermal wind, is created by the temperature gradient. So in this sense, I think the mission will provide a lot of information about dynamics, for example, jet stream and so, which then couples down to weather and regional climate. So I think there will be some significant contributions.
All the way back.
Hi, I have a question. I'm Eleanor Freckle-Williams from the National Oceanography Center. I have a question about variability and whether the repeat sampling of the instrument is going to be sufficient to look at variability, which I think is relevant to the dynamics as well as the mechanisms that you might be looking at. So do you have a sense of, you said that the radiative forcing responds very quickly to the properties in the atmosphere, and the atmosphere, of course, changes very quickly. Is aliasing going to be a problem in trying to conclude some of these big questions about climate uncertainties?
I think for this work of looking at the feedbacks directly, we will average large areas over like periods of a month or so. There is literature about this. For example, there's nice work by Mark Zelinka testing the fed mechanism in this way by looking at the tropical mean over the natural variability on the monthly scale. You can see how the clouds move up and down. It's another way to look at these feedbacks in the upper troposphere that we are talking about here. So we can do similar studies with this fantastic new data set.
So this is the last. One more question somewhere over there.
My name is Bernardo Gozzini. I am a sole director of Consortio Lama. I apologize to all of you because it's a comment, more a question than my speech. Because tomorrow morning I can't attend the meeting. I have to stay in Italy. There is an important meeting of the new agency, Italia Meteo, and there is the meeting of a steering committee where we start to discuss the strategic guidelines for the new agency. I want only to stress the strong interest of Lama Consortium in this mission, and above all, to understand what is the impact of this new measurement into the meteorological model for the assimilation. 2 words about Lama. Lama provides operational forecast for civil protection in Tuscany and Umbria, and for Italian Coast Guards, and also for different private and public bodies. Therefore, for this runs different operational model chain and for different kind of services. Therefore, we are very interested into all the information about the UALTS, about, for example, the stratospheric intrusion, for the development of the wide and very deep low system in this part of the atmosphere. And also, perhaps the forum data can have impact on the statistical methods used for monthly and seasonal forecast.
Could you please formulate your question, because this is our last question, so we're already running over time.
I finally tell you only what happened in Italy. In last June, excuse me, okay. I think it's important. I have to apologize to you but tomorrow I can't attend the meeting. Excuse me, but I go fast. Only to say that in last June, 100 of Italian scientists have addressed the letter to the highest offices of the Italian state, in which they claim that the uncertainties on the climate models used to explain the climate change and the future scenarios are so large. Therefore, they bring in question the need for a policy focused on a drastic reduction of fossil fuels. Quindi, a new open letter with opposite conclusion have been signed by a few hundred scientists and this published. But this confirms and also testifies the importance and urgency of having data that can refute these doubts and reliably assess the anthropogenic source of the ongoing climate change and its strains, also in relation to the Greta wars. Thank you. Excuse me.
Okay, thank you so much. So I think this is the lunch break now, unless Bertrand wants to say something.
Thank you very much, Hilke. Thank you very much to the whole forum team for answering the questions This was a little bit of a rehearsal, and we will have another one this afternoon for tomorrow. So everybody who has not been given the chance to ask the questions, there will be an extended opportunity tomorrow to do that. And from our experience from today, just now, please ask questions. Okay? We now have lunch break. I propose to cut the lunch break a little bit by 10 minutes. I don't want to make it as difficult as last time when I offered you 0. So we will reconvene here at 1400, 2 o'clock. So please be on time, and please give the other mission the same attention as you did for Forum. Thank you.